Good morning. Pretty bright up here. I can hardly see any faces, so typically sitting in front of a monitor, not a bank of lights here. I see Simulia did some background on my bio. I was going to tell you a little bit about myself, and just so you know, I'm basically a sit-at-the-desk practicing engineer doing analysis. Really enjoy it. But it's really nice to be here today, and what I'd like to do is to tell you about 3M in a multiple number of ways here, and kind of lead you through what the company is, some of the interesting characteristics of it that we find. And the way I'm going to do that is first to start to talk about the technologies of 3M, which is the foundation that we build our products on and our innovation on. I'll talk about the business side of 3M, which is the process by which you bring those inventions up and market them and sell them. That'll be the first half. The second half of the presentation, I'll concentrate on the technical side, giving you an overview of the modeling and simulation arena from a higher level, and then finishing off with some Abacus examples. So we call ourselves an innovation company, and really what we're out to do is to sell products to make money. You've all seen and probably used some of our products, Post-it notes, masking tape, sandpaper, those kinds of things. It's in an effort really to improve people's lives and to have you guys move your businesses forward, your lives forward. 3M is really a connection-oriented company, and what we like to do is to do things in a manner of collaboration to solve the problems that we are working on. Interesting, it's not a siloed company. It's not a company where people hold things at their desk or in their mind, but there's quite a bit of sharing that goes on at the technical level, at the management level, across divisions, across technologies. And where that comes out in innovation is that when you start crossing the technologies and the markets and the ideas, you get some really interesting results, all based on our technical platforms. It's at least in St. Paul, where 3M is based, there's a lot of very curious people, a lot of highly educated, geeky kind of people, chemists, scientists, engineers, those kinds of folks. So together, achieving more. Again, we like to focus on tackling problems for our customers, and working together is a way to do that. What I'd really like to point out with this slide is that, just to give you an idea of what 3M looks like, about 84,000 people. It's really all over the world. We sell products in 200 countries. We have operations, some kind of a building in 65. The magic, the key part of 3M is held in the 46 technology platforms that you see listed. And driving that are what we call our market businesses. These are businesses that hold specific divisions, product divisions, and those sit on the technology platforms. And 3M spend quite a bit of money and effort prioritizing the funding of our R&D organization. Even in these slow times, we've put a lot of money into that group to help work on innovation. Okay, here we go with some of the brands. Hopefully most of these are familiar to you. The 3M is the key brand, and then we have our supporting brands, Post-it notes, let's see here, the Scotch tape, sandpaper, so on and so forth. Surprisingly, these brands are what you see as consumer goods, although Scotch really delves deep in some of our other products as well. An interesting fact is if retail products only comprise 15% of those that we sell. The other parts of our products are buried in industries and really out of sight of the general public, so to speak, although you do run across them all the time. So I've kind of alluded to this, the magic that happens in 3M is in regards to our technologies. And it may not be a surprise that in a technology company that we have our own kind of geeky version of the periodic table of elements. In this case, we have our examples table, and these are made up of our 46 different core technologies. This is really where innovation in 3M comes from. I don't know how well you can see those. Hopefully you can read some of the little titles, but these technologies are shared across the company. They're not really owned by any one division, although some divisions may be the primary developer of it. They can be interconnected in 1, 2, 3, or 4 ways or more in terms of the technologies to create new and innovative products and processes. And then some of the market ideas that sit on top of these products also can be intermixed to create some new and interesting ways of creating new products and some ideas. To give you an example of how that works, I thought I'd pull out microreplication. This is one of 3M's key technologies. Microreplication was first started by some scientists coming up with a way to very interestingly put grooves into plastic. And some of you who may be my age will remember the overhead projector. That was one of the first applications where you had a bunch of concentric circles, basically a Fresnel lens in a thin plastic sheet that was used to transmit the light up and give you the image on the screen. That was a great product. I don't know that you see that much anymore. We have these nice electronic projectors, so that's kind of gone by the wayside. And personally, I don't miss creating those slides and having to put slides on the projector and take them off. But as time went on, the overhead projector, there's a newer one than the one my 6th grade teacher used. Some scientists came up with a way of, instead of just refracting light for the Fresnel lens within the overhead projector, they came up with a way of refracting and retroreflecting light, and they came up with what's our diamond grade sheeting product, as you see on those signs. Just about anywhere you go in the world, you see 3M's diamond grade sheeting. This is a step change from our earlier retroreflective sheeting. This is about 3 times brighter than what you see with standard glass bead stuff. So very, very interesting. And the little green picture in there is a micro scope picture of what those little cube corners look like that retroreflect the light. As time went on with microreplication technology, the engineers and scientists started looking into other applications. They got into the use of magnetic recording LCD displays, as well as abrasives, and we'll talk about that a little bit more. One of our big game changers for 3M was something called brightness enhancement film, BEF. BEF is something that all of you have seen and might be seeing at this point. I know the screen that I'm looking at here might be a BEF product. Brightness enhancement film goes on televisions. It also goes on a lot of Apple products. BEF is a wonderful product in that it helps brighten displays. In the early days, it was as much as 2 times brightness over what you would get over competing technologies. What this did for some of our customers is that it obviously made screens brighter, it helped with resolution, but more importantly, it decreased power requirements. The brightness enhancement film became a big player for us. We made a lot of sales in it. And so on and so on. These connections keep going. People keep thinking of new ideas on what to do with some of our products. So with microreplication, this had also branched out into adhesives, microstructured adhesives. So there's one thing about just laying down adhesive in a nice flat strip, but there's also something about putting some interesting features in that adhesive to give you some kind of response or some interesting characteristic of that adhesive that you couldn't get otherwise that came out of microreplication. Drug delivery, we have some interesting micro-replicated parts for our drug delivery business. Abrasives is another game-changing implementation of microreplication. Our Cubitron 2 product is a structured abrasive material made from a ceramic sol that's cured into perfect shapes. We design and create these ceramic shapes so that instead of crushing and gluing rock and other kinds of minerals to make sandpaper, we're doing the same thing with these perfect shapes. And what that's done with our abrasives business is revitalize it, making products that you get it out of the box, it's cutting perfect, it's making a perfect cut right off the bat, and it continues until the very end of its life when it just falls off, has a much longer lifespan. Maybe that's not a good idea, making products that live longer, but it's a much better product. And that's going very, very well. So I think the corporate line here is that you can't go 3 meters usually without seeing or touching some kind of a 3M product. I like to say you can't really swing a dead cat without hitting a 3M product. And where you see that is in aerospace. We had protective films, tapes, glues, adhesives, all kinds of things. A place that you don't normally see it, the medical office, many, many different products there, wound care, surgical drapes, scrubs, antiseptics. It's in your teeth, your restoratives, your crowns, and so forth. Spray, face masks, paint spray, scrubbers, probably all hopefully have Scotch-Brite scrubbers. We do quite a bit of light management. We're in the power industry. Some of the cables that you see, high-tension power lines, are 3M. You see the signs there. The automotive industry is one of our longtime partners, marine, and it goes on and on and on. 3M products are all over the place, and I've been with 3M 22 years, and it's easily not a month goes by when there's not a new product, it's not a new process, or even a new division that comes up, or a division merges into another one where something's changing. It's hard to keep up with what's going on with the company. It's really, really kind of interesting. Okay, I hope you can stay with me for a little bit. I know this front stuff is a little bit boring, but I mentioned 65 countries where we have facilities. Marked in red are where we have the sales and marketing organizations. Blue is manufacturing, and that's increasing. Where we spent a lot of money in recent years bulking up our manufacturing operations overseas. In addition, our R&D technical capability overseas. Those are sites that we call super hubs, places capable of producing more than just a division's worth of product, but creating their own products for the region in which that super hub is located, trying to get closer to the consumer. Some of the statistics here on the company. Most of our sales are not in the United States. We're going to very quickly approach 70% here. An important thing to note, R&D $1.6 billion. We also spend about $1.6 billion on capital improvements. I believe that's the number for this year, and that's going to keep going up. It keeps people like me employed, so I like to see that. 3M, as you saw in some of the earlier slides, is a curious place. We have a lot of people who really like to invent and combine those technology pieces into new and exciting things. So there's quite a bit of patent activity, and that's really a requirement. That's an expectation of the people in the technical community, is to keep your Technobook current, to submit your records of invention, and to work on patents when appropriate. We're a blue chip company, for what it's worth. And from the business side, we have our 6 businesses that oversee and keep everything on target, move our products out the door. All right, advance. Okay, talking about those businesses a little bit more specifically, our big gorilla in the company is the industrial and transportation. These are the guys that own the tapes, the adhesives, and so forth, sandpaper, the birthplace of 3M. Consumer and office, for those who like Post-it notes, keep buying those Post-it notes. Those are out there in the consumer and office. Display and graphics, we talked about some of those products earlier. Healthcare, again, a little bit of a sleeper for those who aren't in the industry. Another quiet one is safety and security and protection services. This is an area who does things like protective films, license plate identification tags, trying to make things secure. Also, library systems, check-in, check-out systems. Electron communications, our sixth market. We do quite a bit in the area of electrical connectors in all stripes. So this is the business side of 3M. These are the groups that have multiple divisions within each. They shepherd the products from infancy up through sales and manufacturing and keep the business together that way and sit on top of all the technology platforms that you saw earlier. I'm going to move into my examples in a bit here, and these are the four markets that the examples are going to cover. The only thing I really wanted to point out here was, as you can read some of these, is that what I like about 3M, what's really fun there, is the collaboration within the company. Very few areas are siloed, very few people are siloed. There's quite a bit of collaboration that goes on between people. It's also a very curious company. People are generally excited at work. They like to explore. They really like to invent. That's something that I found very, very interesting when I came to 3M and enjoyed that quite a bit. Hopefully you want to keep going on that. So let's move on to something that's perhaps a little bit more down the sweet spot of this audience, which is more the technical side. I'll talk about predictive engineering and modeling. As you see, it's got a spot on one of our core technology blocks here. This covers a wide range of modeling and simulation, everything from the structural, thermal, fluid flow that you see in the Abacus product, all the way up into some fairly exotic things, at least in my mind, of numerical methods that you can use to solve problems. So beginning at the very smallest size, and these first three slides are kind of chemistry, physics thing. Don't ask me questions. Fortunately, you can't. I can't explain them, but these are really, really strange things that people do at 3M. So quantum mechanics, these are dealing with electrons. What can you do with electrons? Reflection properties, electronic properties. We're into nanoparticles quite a bit. How those interact, very important. And we have a group working in that area. Moving up to the atomic level, this maybe is a little bit more traditional. From an academic standpoint, we use both academic and commercial code for this kind of things. If you can think of all the ways that you need to put atoms together to make chemicals and how chemicals interact, this is a tool that people can use to figure out how to do that and why things do things the way they do at that scale. Not surprising at 3M, we deal extensively with polymers and polymer products and derivatives. The mesoscale, it moves up a little bit from the atomic scale, and you're trying to figure out, again, how to make things work. A little bit bigger, a little bit less resolution than atomic. Okay, now I'm getting into something I have a little bit more familiar with. The slide on the right, that's an output from an Abacus simulation. We've tried the acoustic module, and it's great to see you develop it. We have a small but powerful acoustics capability with 3M around particularly Thinsulate. You probably had it in your sweaters, your jackets to keep you warm. Thinsulate also makes a great sound deadener. So we've put that toward the automotive industry and have sourced it through a number of different vendors. The analysis at the right was done on an air purifier. So for those products that we have that make noise that we don't really want to make noise, or we're going to somehow mute that noise, the Abacus is a tool to use there. Surprisingly, quite a few of our products at 3M include electromagnetics. We have a strong presence in RFID, capacitive sensors. We're a leader in library checkout systems, which are magnetic in how they work. In the medical space, we sell all sorts of products, one being an electrosurgical grounding plate that we've done an analysis on here a few years ago, making sure that as you're grounded for surgery that involves powered equipment like electrically cauterizing knives that you don't get short-circuited and electrocuted on the table. Optics. This is a very, very important part of 3M. As you saw on my slide for micro-replication and how that's developed. Quite a few of our products are optical in nature, and we do use quite a bit of different kinds of software, academic and commercial software, to do ray tracing, everything from down at the nanometer level for light reflection and refraction on up to very large devices like solar systems, solar arrays, and so forth. So we have quite a few lighting products, and that's a growing area. So as far as the resources that we have, I thought I'd include this slide. I know when I'm sitting in the audience listening to a talk like this, it's nice to know in the different companies, well, what is your environment like? What do you work with? What are your tools? So I thought I'd mention that. We really use a wider range of tools from the commercial code, such as Abacus, competitive tools, the Abacus. We won't mention their names. So we have both those commercial tools. We have a lot of academic tools. People, as they come out of school, they're familiar with some tools that they've used that were developed in school, and they bring that capability and those tools with them. We're also interested in open source tools, and we have those available for solving some of our numerical problems and simulations. The areas highlighted in red are those that I'm going to have specific Simulia-based examples about, and I've already talked a little bit in the black examples. So what we find is that there's no golden tool out there. Unfortunately, every tool that we have has their own capability and so forth. Many times it's not uncommon to use more than one package to get through a problem that we might work on. As far as our compute resources go, it's kind of an eclectic mix. We have an IT organization that supports the 78 node cluster that you see, as well as the 96 core SMP computer that you've got there. The two in the middle, the two 6 node clusters, are for the engineering analysis group, which I'm in and support, and that's just for our needs. From a load balance, load sharing kind of application, we use the PBS queuing system. It's pretty handy. In my particular cluster, one thing we did was to install graphics cards in a couple of our compute nodes directly so that we can have direct rendering. We find that the desktop is really almost too small for some of the models we do, both in the CFD area and the structural analysis area. Difficult to display, difficult to get performance out of it. It's been very handy to do that. And the last piece I wanted to mention is that many times we work on projects that are one of a kind. It's not too often that we repeat ourselves or have the chance to repeat ourselves, but there are those instances. In particular, for some of the products that we sell, our customers would like to have the capability of analyzing how they would use our product that we supply in their item that they sell. For instance, the in-ram sheeting material which we sell to the automotive industry, which goes and wraps around catalytic converters. We have a number of different programs. That's one of them, where we supply a web-based interface to both internal and external customers, where they can input their parameters, say submit. That goes off to one of the compute systems. The job is solved, a report is written, and that's emailed to them. So for those specific instances where we can repeat ourselves, that's been a very handy tool and something that was developed internally. The groups that we have doing work, 2 full-time groups, the engineering analysis group, which is the one that I'm part of, and 2 folks here from EA with me today. Another person here from the PE, Predictive Engineering group, comes. These groups are both about 8 people each, roughly. And these are full-time people, always working in the analysis area. For the chemistry part, there are some full-time people working on some of the chemistry codes. I really don't know the exact count right now. And then scattered around the company, we have onesies and twosies, people who do part-time work as needed to solve the problems that they need. And we all share the tools, we share the resources, and get to know each other as well. The US is pretty much where the modeling and simulation started in 3M, and it's growing. Recently, we've just added Korea to the Abacus family. They were added to our RAN. We have quite a bit of work going on in Japan, also Canada, and I've listed, for those who came from Texas, hopefully you'll be happy to see that I've listed that separately. I know some think it's really their own country. Thank you. My in-laws are Texans, and so I was trained how to deal with that. Okay, let's get down to the specific Simulia examples real quick here. The first one is a 3M helmet. This is a protective device. This is something that you would wear in a specific environment. We have a number of different varieties. This one has a face shield, which can kick up. You can pull it up. It's got a shoulder shroud and a neck shroud, clear visual visor, and what you don't see is up in the back of the helmet, the arrow's pointing to it, you have a hose coming up from the item that's sitting on the right. That's just the straps that hold a powered device and a fan and a filter media. And we like to sell the filter media part, and this is how this all gets going. So this is a powered, full-powered respirator helmet, and you can wear this in specific environments intended. From the modeling standpoint, why I wanted to show this is that this is an item that used to be developed pretty much as from an experimental standpoint. People would come up with a design, they would have it molded, they would test it, they would try and pass the ANSI tests by doing impact and squeeze tests, and it would take a long time to do the work. This is an area where modeling and the tool Abacus has come in very handy. This is the first generation helmet that was modeled. This is our baseline. What you see is an impactor. It's a ball that's being dropped. It's got a specific velocity when it hits the top of the helmet. And what we were doing with this was to find out and calibrate the materials to performance. We knew from experiments just how this helmet worked. We knew in the upper right-hand graph how much force was transmitted to the neck and head from the impact over time. The lower right-hand plot is how much deflection, or how much clearance, I should say, the inside bottom of the helmet has between there and the top of your head. It's important that the helmet doesn't bottom out on your head. And then the plot in the lower center are energies. This example is provided by Dylan, who characterized the materials in the helmet. You have the outer shell, you have the straps, which connect to the and go over the head form, which isn't displayed here. The hangers connect the straps to the inside of the helmet, and up inside is an air duct that you don't see. A lot of the materials were characterized as either viscoelastic or hyperviscoelastic, and Dylan spent quite a bit of time getting this right, the techniques to measure the materials and get those looking well, so that he had good correlation between this particular product in the model compared to the what was measured. And what's key to that is all of that work that went into that baselining was then transferred to the next generation. Here you see a slightly different helmet. The purpose of this one was to keep up with the Joneses. It's got a little bit cooler styling. I don't know if you can see that, but it's a little bit lower profile, so that looks better. The particular force and displacement responses are very similar to the earlier helmet. But what's really novel about this, and this is where the power of modeling comes in, is that the first helmet, as it was developed and done exclusively through experimentation, took 10 years from start to finish. Extremely long time. That's really not realistic and competitive. Dylan was able to get in with this division, work with them closely, developing the techniques and the modeling capable of taking a new design, and they went from conceptual idea to putting it on the shelves in 3 years. It'd be nice if you could do it in a year or less, but 3 years is market improvement over 10. The early models of this helmet used to run overnight. Dylan is our master token user for problems just like this. The latest models with some of the technologies embedded in Abacus take about an hour to run. So very quick, you can very quickly figure out how some of these things are going to work. Other pieces that go with some of these projects that we have, in particular for the helmet one, is the face shield has a requirement in addition to the impactor hitting the top of the head and also a squeeze test, all of this done at different temperatures. This is an 8mm steel ball that's hitting the eye level of the face shield, and you have a requirement to make sure that at the eye level every 20 degrees that there's no penetration and that the face shield will stay intact and so on and so forth. So what you see is Dylan's work here showing the stress and response of the face shield. So this adjacent part to the main helmet, very quick and easy for Dylan to add that. Now Dylan was so successful with the first helmet, these guys really started to like him. He was saving them a lot of time. Here's another example of where modeling is integrated in other things. This isn't the powered respirator, but this is a regular breathe-through respirator, and you can see some of the equipment with it. It too had an impact thing that it needed to do. A nice thing about using Abacus with this is that you have both the interesting properties of the face shield, but also the rubbery response and the seal around the edge there. So this is a completely sealed face mask. Very important that if you have an object hitting or trying to penetrate your face shield, that you don't have any kind of leakage on the side. And that's what Dylan was checking for here. Very quick to do. In our Austin divisions, we have 2 or 3 divisions that work on electrical, electronic type products. 3M is into connectors in a large way, and we do quite a bit of analysis on these. A simple analysis that I wanted to show you is this is a Sata Connector, and it's really a straightforward analysis here using standard. What we're doing is we're showing the insertion and connection between the male and female parts of the connector. You can get simple outputs such as stress, strain, performance, how the connector is going to work in itself. Really all what we're doing here is we're trying to figure out what the contact stresses are between the parts so that we can figure out how much plating to put on the connectors. The least amount of plating that we can put on, the lower the cost of our connector and the cheaper product is for the customer. I also wanted to show this from scale size. Face masks are one size. Here's a smaller one. We've done even smaller than this, typically now. This is purely a fun slide. This is real. A number of our products are in the form of film, and some of our films are protective films. We do products that are good for hurricane protection. You wrap your windows with this film, and if you have high winds or objects hitting the films, the windows stay intact and together. We also have blast protective films or much stronger types of experiences. This is a project where they were thinking of a prototype, and they wanted Dave Lindeman, who's in the Predictive engineering group, to take a look at this from a modeling standpoint. And this was one of the first applications that I saw where we were using a damage criteria with a brittle material coupled with a connection with the underlying film and trying to capture the whole response as what you see are 2 2x4s hitting the window. So this would represent hurricane stuff, pieces coming off houses and whatnot hitting the window. The fun part of this project was that we actually made a 2x4 hurling machine, and we're able to try and correlate what you see here with actually what was going on. Okay, a sweet spot of 3M is tape making. This is a really what looks like a very simple model here, but this is packed with all sorts of technology. The adhesive in this is viscoelastic. Everything else is elastic. What we wanted to do here was to go from our existing peel model and put it into Abacus to give it a little bit more oomph. And of particular interest is that, again, using micro-replication, we are micro-replicating the adhesive, having places where there are cutouts. Depending on where these cutouts are on this product will determine how the product performs, how much the peel strength is, what its behavior at different peel speeds, at different peel angles. This required quite a bit of effort on the part of Chowdee. The adhesive part and the failure criteria had to be created with user subroutines to make this match reality. Quite a bit of time was spent on this. If you look at it from another perspective, here's some features here. As you pull it up, it kind of snaps as it comes off the surface. And then you have specific peak forces as each of those disengage. And you can investigate however many permutation and commutations of this that you have. Why is that important? Well, you can create a map. You can create a listing of if a customer wants a specific peel force, you can figure out how much adhesive you need to put on it to get the performance that they need. These are fairly flat, but the combinations are endless, and what we find is that customers have lots and lots of requirements. So the more that you understand your product and the quicker that you can figure out how your product will perform under given geometries and conditions, the better you can respond to it. And Abacus, in this case, has been a great tool for us to figure out tape, in particular tape with micro-replicated features. The next example is one that showcases capital equipment. I'm in a group that primarily focuses on capital equipment, where our predictive engineering group focuses more on product design. They each have their pros and cons. This is from an analysis and analyst viewpoint, but they're all very interesting. In this case, this is getting up to the larger scale of things that we use size-wise to model with Abacus. This is about on the order of 15 by 20 by 30 feet. This is a very large support frame that's holding a precision piece of equipment that's making a product with features on the scale of 11 nanometers. So what's important with this example here, and we do this routinely now with Abacus, is for these very large support structure, we want to make sure that the natural frequencies of this stay above a certain frequency or a certain set of frequencies. That's important because if you have too much movement, we see that in our product. And when you have very, very small nanometer size features, that shows up in a big way. So the arrow's pointing out where a large mass is of the key piece of technical equipment that's mounted in this station. The yellow markers are showing all the ties. I got to point out that a enhancement request, Jennifer would like to have done a tie connection with everything, but this actually had to be done manually, and it took a little bit of time for her to connect all these pieces, both solids and the continuum shells used in this model here. And what you see is the output. This looks like just about any other kind of modal output that you've seen before, but what we do is we get to understand the, I'm going to back up because it's going to make people sick. I can't watch that slide, but getting to understand those modal frequencies and staying out of particular behaviors are important. And we couple our experience of what we've done in the past and what we know in the past to what we're designing here in this case. Okay, Jennifer submitted this example here. This is a solar collector. The important part of this is the solar film inside the parabolic piece. And the analysis is to make sure that this device withstands either an 80 or 200 mile an hour wind. I think the 200 mile an hour wind was something of more of an interest than a requirement. So here's the structure. It stands about 6.5 feet tall when it sits on a pedestal and you have wind coming at it from either direction. There is a bracket on it in the center and the pedestal where things are connected, and you want to make sure that these are okay. This is our first production implementation, I think, of Abacus Structural with CFD, and this came out really well. It happened pretty quick, I think relatively speaking, pretty easy to do. This is a cross-section of the domain for the CFD part. If you run through it and solve the problem, you see the flow lines. And rather than take some kind of a book solution for what the pressure would be on the parabolic part and do the stress analysis, we took this output straight from the CFD solution into the structural part, and you get your deflection. If you really wanted to, you could also see how much the parabolic part's deflecting and figure out what your loss of efficiency is for your optical capture is. But in this case, you're really worried about the bracket, the structural supports, and whether or not this is going to rip off your roof or not. The final example that I want to go through is another one that's kind of a sleeper in terms of technology. Quite a bit of what we do at 3M involves web processing. So Post-it notes, tape, films, all those kinds of things that are pretty flat are done usually wide and fast. So we make it by the yard and sell it by the inch is how we typically refer to that. In some cases, in this one we have a coating step, it may be a casting step, pressure could be involved. You could be laminating, combining different materials together at different temperatures, pressures, and so forth to create whatever novel product that you're creating. In order to do this well, you have to understand the physics of what's going on. Sometimes it's the physics of filling, it's the physics of coating, it's the physics of lamination. All kinds of problems creep up when you're dealing with web-based processes. We've had a group that's done a lot of specific modeling in this area where they've modeled one specific part and they understand it well. But to be able to do a whole line where you go from start of raw materials to finish and tie it back to the performance of the product, we've never done before until now. And this is our eyesight example. This one's hard to read, I know, but what you see is we have a portion of the code. This is an internal code that we use to solve the characteristics of the web thermally. We have a code step. I'll call it a code step. We have another code step in here. These are internal codes that we have, and then a whole host of other calculations that we're doing to figure out that given set of process conditions, is this what we want? Is it coming out the way that we want? Is it going to be a good product? And if it's not a good product, what does that product look like? So when you run it, this is a case where every place that you see a colored dot is a rejection. It failed for some specific reason. It had a defect. Could be a coating defect, a filling defect, a temperature defect, a material property defect because it wasn't processed right. By using eyesight and running through this and checking, you start to see areas that open up. That gray area with no dots, that's what we want to see. This is what we call a process window. We stay outside or inside of the dotted areas, and those are the places where we can run this line to make the product where it's going to come out the way that we want to run it using our codes. Here's a final one where we're figuring out just how to turn the knobs to make this stuff run well. Why is this important? This is important because what used to take literally years to put together some of these models, and then what would take months to do some of these simulations, now can be done in a matter of 3 or 4 hours. So experimentally, you can do these web-based processes, but for those who do web-based stuff, you know that it can be extremely expensive on the order. In this case, just a simple tooling change could be on the order of $30,000 to $50,000 if your tool has got just the wrong way and it just wouldn't work after all. So if you can do it numerically, everyone knows the story there. It's a good deal. This is the end of the technical part and pretty much the end of my presentation. I just wanted to review. We talked about 3M from our technology standpoint. If anyone wants to talk about that afterwards, I'd be glad to. Hope you have an understanding of our businesses a little bit, maybe a little bit different structure in some other companies you know, and then the technical side of it in modeling and simulation. And for those here who are from Simulia, I have some words for you. What's really important for us and 3M is that you keep working on technology. technology, technology, technology. I know you have your own drivers for your business, but what you put into your code is what allows us to do what we do on our end and make our project or products. Where you really stand out strong is that you have the leading and disruptive first principles technology embedded. At least I hope you can still be disruptive in it. Usability is very important. As CAE has matured, more people have come on board in 3M and have started using Abacus to the detriment of some of our other codes. And now we have a real crunch on Abacus tokens. If you and Simulia can help me out and give me more tokens for the same price that we pay now, I'd really be appreciative. Someone like that a lot. I like that. And then rapid response technical support, very, very important to us. Abacus can be hard to use. It's nice to have people who are responsive, on a first name basis. We do that with your Woodbury, Minnesota office. Very, very helpful. So with that, I'm done. If anyone wants to talk later, I'd be glad to. Thank you for being patient listeners.